Hello my dear wonderful genius students, I'm back again with a new video. This is lecture number 17 on complex analysis. Today I'm going to teach you a very important topic which is Cauchy's integral formula. Students, as you know, in my last video I was explaining Cauchy's integral theorem. So therefore, before going to this topic, I just want to mention under what condition we should apply Cauchy's integral theorem as well as under what condition we should apply Cauchy's integral formula. Students, if there is no singular point within or on a closed curve C, then we should apply Cauchy's integral theorem. However, if there is at least one singular point within or on a closed curve C, then we should apply this Cauchy's integral formula. Now, let me read the statement of Cauchy's integral formula. According to this formula, if f of z is analytic within and on a closed curve C, and if A is any point inside C, then f of A is equal to 1 by twice by I integration along closed curve C f of z divided by z minus A into dz. Now, let us understand what is the meaning of this statement. Students, suppose we have a closed curve C, and within this closed curve C there is a singular point A, and apart from that there is a function f of z which is analytic within and on the closed curve C. By analytic I mean to say that this function f of z satisfies the CR equations within and on the closed curve C. If these two conditions are satisfied, then value of the function f of z at z equal to A will be equal to 1 by twice by I integration along closed curve C f of z divided by z minus A into dz. Okay? Now, let me derive this formula. So, here the function f of z divided by z minus A, gz is equal to f of z divided by z minus A is analytic at all points except at z equal to A. Next, we draw a small circle C1 with A as center and radius smaller within the bigger circle C. So, now we draw a small circle C1 with A as center and R as radius within the bigger circle C. So, after drawing this small circle C1, we have seen that the function gz is analytic at all points in the region in between C and C1. So, therefore, we can apply Cauchy's integral theorem. So, first let me write these points. Since gz is equal to f of z divided by z minus A is analytic at all points in the region between C and C1. So, by Cauchy's integral theorem for multiple connected region, multiple connected region, we have integration along closed curve C, f of z divided by z minus a dz is equal to integration along curve C1, integration along curve C1 f of z divided by z minus a into dz. This is equation number 1. Suppose let us putting z minus a is equal to r into e to the power iota theta. So therefore dz is equal to r into e to the power iota into d theta. Substituting these values in equation number 1, we get integration along closed curve C f of z divided by z minus a dz is equal to integration along curve C1 f of z is equal to a plus r into e to the power iota theta, a plus r into e to the power iota theta divided by z minus a, which is equal to r into e to the power iota theta, r into e to the power iota theta into dz. Dz means r into e to the power iota theta into iota into d theta, r into e to the power iota theta iota into d theta. So after simplifying, we will get iota integration along curve C1 f of a plus r into e to the power iota theta into d theta, equation number 2. Now let us check what will be the form of equation number 2 when the radius of the small circle C1 is very small. So if r tends to 0, then equation 2 takes the following form. Integration along closed curve C f of z divided by z minus a dz is equal to iota integration along closed curve C1 f of a d theta, because in this case we put r equal to 0. So after simplifying, we will get integration along curve C f of z divided by z minus a into dz is equal to iota into f of a integration, limit will be from 0 to 2 pi, 0 to 2 pi d theta. So after simplifying this part, we will get twice pi. So finally we will get integration along curve C f of z divided by z minus a into dz is equal to twice pi I f of a. So after rearranging, we will get f of a is equal to 1 by twice pi I integration along curve C f of z divided by z minus a into dz, which is proved. Next, let us learn another important topic, which is Cauchy's integral formula for derivative of an analytic function. First, let me read the statement. If a function f of z is analytic, in a region capital R, then its derivative at any point z equal to a of R is given by f prime a is equal to 1 by twice pi I integration along curve C f of z divided by z minus a whole square into dz, where C is any closed curve in capital R surrounding the point z equal to a. So, let us derive this formula. Proof. We know according to Cauchy's integral formula, f of a is equal to 1 by twice pi I integration along curve C f of z divided by z minus a into dz. Equation number 1. Now, differentiating equation 1 with respect to a, we get f prime a is equal to 1 by twice pi I integration along curve C f of z del del a of 1 by z minus a into dz. So, after differentiating this part with respect to a, we will get f prime a is equal to 1 by twice pi I integration along curve C f of z divided by z minus a whole square into dz, which is proved. Next, please note down some important points. So, note. Similarly, we can show that f double prime a is equal to 2 factorial divided by twice pi I integration along curve C f of z divided by z minus a whole cube into dz, and nth derivative of a f to the power n a will be equal to n factorial divided by twice pi I integration along curve C f of z divided by z minus a whole to the power n plus 1 dz. Okay? The last topic that I am going to discuss is Cauchy's inequality. So, first let me write the statement. If a function f of z is analytic, within a circle C, that is modulus of z minus a equal to r. So, the radius of the given circle is capital R and center of the circle is at A. And if modulus of f of z is less than or equal to capital M on C, then modulus of f to the power n a is always less than or equal to capital M into n factorial divided by r to the power n. So, this is the statement of Cauchy's inequality. Please try to derive this part by yourself. This derivation is already available on the book H.K. Das. Page number 649. Okay? So, this is all about today's video and I hope that you have learned a lot from this video.